Hi everyone. Today we'll embark on a fascinating journey into the world of number theory, exploring the arithmetic of congruences and linear congruences. These concepts are fundamental in understanding how numbers relate to each other in modular arithmetic. Congruences are a cornerstone of number theory. When we say A is congruent to B modulo M, it means that M divides A B or A and B leave the same remainder when divided by M. This concept extends to arithmetic operations. That is, when A is congruent to B modulo M and C is congruent to D modulo M, then the addition, subtraction, multiplication, and exponentiation follow specific rules under congruences. Unlike other operations, division in congruences requires the divisor to be coprime to the modulus. For example, when trying to divide 2x by 2 modulo 6, we find that the greatest common divisor of 2 and 6 is not 1, making direct division invalid. Let us find the unit digit of 7 raised to the 100th power using the concept of congruence. Note: a number's last digit is the remainder when it is divided by 10. Now, let us check the powers of 7. Note that 7 raised to the power 4 has unit digit 1. This means when 7 to the power 4 is divided by 10, it gives a remainder of 1. In the congruence form, we can write this as 7 raised to the power 4 is congruent to 1 modulo 10. Taking exponent 25, we have 7 raised to the power 100 is congruent to 1 modulo 10. This implies 7 raised to the 100th power has a unit digit of 1. Great. Now let us consider another example in which we have to find the unit digit of this expression. Note 7 to the power 4 leaves a remainder 1 when divided by 10, and hence by taking the exponent 5, we get 7 to the power 20 will also leave a remainder 1 when divided by 10. Good. Now, as 7 to the power 3 gives a remainder 3 after dividing by 10, therefore by multiplication operation in congruences we get 7 raised to the power 21 gives remainder 3 after dividing by 10. Great. Similarly, 3 raised to the power 4 gives a remainder of 1 when divided by 10. Taking exponent 11, we get 3 raised to the power 44 is congruent to 1 modulo 10. This result, together with 3, is congruent to 3 modulo 10 gives that 3 raised to the power 45 is congruent to 3 modulo 10. Now adding both expressions, we find that the sum is congruent to 6 modulo 10. Hence, the answer is 6. Let us move to another topic, linear congruences. Linear congruences are equations of the form x congruent to b modulo m, where a, b, and m are integers, and x is the unknown integer. These equations have solutions if and only if the greatest common divisor of a and m divides b. Let us consider an example of 6x congruent to 9 modulo 15. Here, the GCD of 6 and 15 is 3, which divides 9. Hence solution exists. To simplify the equation, we divide the entire congruence by the greatest common divisor. Next, we find the modular inverse of a by d. That is, we find y such that a by d multiplied by y gives 1 modulo m by d. Then, we multiply the congruence by y and hence we get x. This technique is essential for solving complex congruences efficiently. Let's solve a linear congruence. 6x is congruent to 9 modulo 15. Here, the GCD of 6 and 15 is 3, which divides 15, and hence a solution will exist. Dividing the congruence by 3, we get 2x is congruent to 3 modulo 5. Now, the multiplicative inverse of 2 is 3. So multiplying the congruence by 3, we get x is congruent to 9 modulo 5, which in turn gives x is congruent to 4 modulo 5. This implies x equals 4 plus 5k where k takes values from 0 to d1.